Okay, if you can hear me, I shall start then.
Yes, we can hear you.
Okay. So the last topic of the class of environmental modeling is related to biological processes, and in particular, we shall introduce our application for modeling algal growth. As I told you, when you think about algae, we refer to phytoplankton. Phyto means vegetable, plankton means small organisms. These are pictures representing the very huge, significant variety of phytoplanktonic species. Phytoplankton has quite complicated structures, as represented by these electronic microscopy pictures, but we are referring to very small organisms, living objects. In particular, we said that when we shall introduce a model describing algal growth, we shall, as always, start by the application of the continuity equation or the principle of energy conservation, if you want. And we may write that the variation in time of the concentration of algae is equal to a series of parameters describing the various processes. In particular, there is a first positive contribution, that is the growth rate, and then there are a series of negative or subtractive contributions that are processes that takes away algae from the algal pool. And then you multiply all these processes for the algal concentration, so that this equation is a first order linear differential equation. And then you subtract, or we subtract, the totality of the algae from by employing a term G that is the grazing term, and that takes into account the fact that the organisms at higher trophic levels feed or chase or eat the organism at a lower trophic level. So with grazing term G represent the connection between the trophic level of algae with the higher trophic level. The parameter appearing to this equation are the first one, the growth rate, mu. This is speed. These are all rates, 1 over time. So there is a first term, mu, the growth rate, that represents the speed of growth of the organisms, minus or the respiration rate, minus the exudation rate, minus mortality, but is non-predatory mortality, so mortality due to senescence or to sickness or to unavailability of resources, minus settling S. Generally, we employ as a currency when we write this kind of models concentration of algae. A, for example, may be measured in chlorophyll A, that is a proxy of a concentration of chlorophyll. It is a proxy of concentration of organisms. Or you may also write the same model by employing, instead of the currency like the concentration of algae, we may employ the abundance of algae. So A may be described as a number in cell per unit volume, cell per liters, for example, number of algae that are present in our system. So this is the very general model for describing algal growth. So now we have to go and give a look to all the terms that appear into the model. First of all, we shall notice that the respiration and the exudation terms are all terms that are strongly dependent on temperature. So in order to describe this, we say that the respiration, or for example, the exudation, is equal to a value at the reference value, at the reference temperature for exudation or for respiration, multiplied by a function of the temperature that is a limiting function. These limiting functions, ft, are all in the range 0, 1, meaning that the function is 1, there is no limitation at all, so you have the maximum possible performance of a process. When f is 0, you have total limitation, so the process cannot proceed anymore. We have also to notice that these quantities like respiration, exudation, mortality, and so on may depend also on the physiological state of the cell. In order to include these, we may complicate a little bit the limiting function. Instead of only including a limitation due to temperature, we may also include a more subsequent function, limiting function, that describes the limitation from the other limiting elements like light, nutrient, nitrogen, phosphorus, carbon, or silicates, and so on. And I recall you again that these f are function that have a value between 0 and 1. When you have f equal to 1, you have no limitation at all. So the system is performing at its maximum possible rate. When f is 0, you have total limitation. So the system is not performing at all. Let's give a look to the term M, non-predatory mortality. We have to introduce this in order to distinguish it from the predatory mortality. Non-predatory mortality refers to mortality due to other causes that are not predations, like, for example, as I told you already, senescence or the presence of any sickness or the absence of some fundamental elements like proteins or the presence of toxicants and so on. So the non-predatory mortality is accounted by this M function, while the predatory mortality, as we already said, is accounted in by the G term, grazing term, capital G term. So the predatory mortality, so mortality due to the effect of predation, is represented by G. This is why we have two mortalities, G, that is predatory mortality due to the upper trophic levels, and M, that is non-predatory mortality. Okay? Concerning the settling, we have already seen a couple of models that you may employ for describing the process of settling. In this case, S is trivially made equal to the settling velocity divided by the system depth h. So this quantity S is a speed that is normalized by the depth of the system. So the higher the depth, the smaller the settling rate, of course. The smaller the depth, the higher the settling rate. Again, the higher the settling velocity Vs, the higher the settling rate, and so on. So S, the parameter S, describes the fact that a significant portion of the algae are taken away by the algal pool, from the algal pool, due to process of settling. So algae that are moving from the water column down to the sediment. Then we shall explicitate the first term, the growth rate term mu. In this term, we include or we hide all the complications or all our understanding of the biological processes involved, and in doing this, we simply redefine mu as a function of a mu max, so maximum value of growth rate at a reference temperature. So you can understand that Trf depends on the species of algae So this is a characteristic of the algae, so at which you have the maximum value of growth rate, mu max, and this quantity is reduced, as always, by multiplying it to a series of limiting or limiting function. One function, for example, describes the limitation due to temperature effect. Another function describes the limitation due to light effect. And then we have another final function that describes the limitation due to the presence or the availability of nutrients. In this case, these functions depends on the concentration of nitrogen, phosphorus, carbon or silicates, and so on. In particular, when we have several effects of limitation, we talk of co-limitation, and there are several ways of combining with this co-limitation effect. For example, one way is represented by this equation, in which you simply build the limiting function due to availability of nutrient by multiplying the different limiting function of the nutrients. So these are all submodels that are defined on the basis of our understanding of the performance of the systems, or our understanding of the relevance of the various processes. And if we have more than one limiting effect, we have a first option is that of multiplying this function. I recall you that this function are all in the interval 0, 1. So by multiplying these, you are somehow trying to take into account for a synergic effect. Or you may also imply harmonic mean, or simply, the most used is probably this last one, in which you have a classical average of a value of the various limiting functions. Another important way of describing limitation is the so-called Liebig's law of minimum. This one, in this case, what you're doing is that you are describing limiting effect, take the smaller of the limiting function for the various parameters of the various aspects. Of course, I recall you that all these functions are in the interval 0, 1. So by taking the minimum, you are accounting for the strongest limitation. Essentially, you are overestimating the limiting effect. Now let's give more a look in detail to the limiting effect due to temperature. So let's explicitate this FT. In order to describe the limiting effect of temperature, we have essentially three different approaches. The first one is the linear function, in which you say you define Ft as T minus the minimum value of the temperature allowed for a particular ice to survive, divided by the reference temperature, which you have an optimum growth, minus the minimum. The exponential formulation is an Arrhenius-like, if you want, which write that the limiting function due to temperature is equal to T theta elevated to the difference between the actual temperature and the reference temperature, or an optimum description, but is the last one, but is a little bit more complicated descriptions. But takes into account for an optimum effect. If we look at these functions, so meaning that if we plot this function as a function of the temperature, we obtain two different shapes. The first one is an exponential shape, exponential limiting. The second one is a linear. And the third one is the so-called optimum formulation for limiting effect. Is this one. In particular, we shall notice But when we are in this range, the limiting functions are very coincident. So in the interval between, let's say, 20 degrees and 25 degrees, but is reference temperature interval for biological processes to perform, the three functions are not very distinct, are not very different. So the idea is that we shall employ a linear description or linear limitation function, linear, sorry. One moment, please. Okay. We may employ a linear description, linear limiting function from the temperature when we have essentially one type of algae in our algal pool, so that we can identify reference temperature, a minimum value, and a maximum value. In this case, so the linear model is quite correct. In general, the more precise model is the so-called the optimum model, so this one, in which we have an optimum function but displays a maximum at the reference temperature. In general, this kind of limitation effects depend from the type of algal population that appear into your system. In particular, this graph gives you an idea of the fact that flagellates at one type of phytoplankton display an optimum behavior. The blue-green also mixed populations, a population in which there are several types of algae, are better described by exponential or linear approaches. In particular, the diatoms, that are a particular type of phytoplankton that depend on the presence of silicates for its growth, are described by an optimum function. So a function that accounts for the fact that there is a temperature, a reference temperature in which you have a maximum growth rate. Okay. One moment. Okay. Allora, as we said, when describing algal growth, we are dealing with systems with living objects that are quite complicated, quite difficult to measure in terms how much, how many, and so on. In this picture, you see a way of measuring the quantity of phytoplankton by employing filters on which you make phytoplankton grow, and then you explicitly manually count the number of cells per unit surface. If you have this kind of representation, then we said that in terms of limitations, we simply employ a set of limiting functions, one limiting function that accounts for temperature, one limiting function that accounts for the presence of light, and a more complex limiting function that accounts for the presence of nutrients. Okay, we have seen these three graphs. Now let's give a look to a limiting function that we may employ to describe a limiting effect due to the presence of light. In particular, in this case...
Sorry, Prof.
Yes?
Can you upload this new presentation on Moodle, please?
Yes, give me one
Thank you.
moment. Ah, yes, you're right. It's not visible yet. Okay. Okay. Now you should see this. Visualize. Okay. And the title is Nutrient Limitation, Growth Dynamics, and Phosphorus Cycle. Can you see it?
Yes, thank you very much.
Okay, let's go on. We said that if we want to describe the limitation effect due to light, we shall explicit FL, so the limiting function due to light. And how do we do that? If we introduce the term linked to light dependence, I is the intensity of radiation as a time day and of the day, when you may build a saturation-like limiting in this first case by saying that the function Fe is equal to I, Fi is equal to I divided KL plus I. In this case, we have a saturation-like shape, that means that this function has this kind of shape, while we may employ a second approach, that is the so-called still approach, or an optimum approach, in which that is the second one that I'm representing here, this one, in which the limiting function has a shape like a bell shape or optimum shape function. Good question. When you write this kind of description, you may ask yourself, what is the optimum value of irradiance at time t? Of course, this value depends on the characteristics of plants or algae that you are describing. So the optimum value of irradiance is a function, is a characteristics of a plant itself. Okay. These are the two shapes that we obtained by employing these two models. First one is the saturation. The second one is the still optimum formulation. The second type of formulation takes into account for a photoinhibition effect. This means that there are some algae or some organisms that are endangered or are depowered by the presence of too much light. So there is a kind of photoinhibition, so that when the light increases too much, after a certain value, the growth rate starts to decrease. While the most utilize a limiting function for light is a saturation-like curve that tends to describe the fact that growth tends to increase as a function of light intensity, and until it reaches a plafond or a saturation-like level. You may recall that these two different behaviors are linked to the two main different categories of plants. We have seen that there are plants that are light stimulated in a continuous growing way, while there are plants that after a certain value of irradiation stop growing. We have described in last lecture this by saying that there are light acclimated and shadow acclimated organisms. Light acclimated organisms are those organisms that have maximum performance when light is strong or when light increases, while dark acclimated organisms are organisms that have maximum performance when there is an intermediate value, or if you want, when the light intensity is at an optimum value in terms of the limiting effect. Okay. Of course, you may recall that another important aspect we have been describing during last lecture is that of light extinction due to the fact that light crosses media, but is plenty of different elements that may perturb the way light propagates. And for this reason, when we write this kind of limiting function, the E is the intensity of radiation at time at a certain given time, t, and at a given depth. This means that if you want to obtain the limitation or limiting effect on the whole depth of ecosystem, on the whole depth of the water system, and on the whole time of the day, then you will have to integrate this limiting function on the vertical in order to account for the different limiting effects due to different depths. And you have also to integrate this on the photoperiod. So if you perform this kind of integration, then you obtain a limiting function, these two limiting functions in which you have parameters like the photoperiod or like parameters like the photoperiod or the depth or the quantity of radiation reaching on the surface of your system. And I recall you that this model, this is an astronomical model. We have already seen this model. In this case, in the case of a saturation, the limiting function has this shape. Once integrated over the depth of the system and over the photoperiod has this shape, while on the optimum formulation, the still formulation, the limiting function has this form, displays this form. So we have seen up to here how to integrate the limitation or limiting effects due to light, due to temperature, due to light and due to temperature. Now we shall focus on the effect of limitation due to the availability of nutrient, what we call nutrient limitation. I recall you that when we think about nutrient, we are thinking on essentially phosphorus, nitrogen, but also silicates or iron. In general, way of combining the effect with multiple limitation effect due to presence or absence of one or more of these elements are in general modeled by employing a Liebig's minimum approach. The Liebig approach, I recall you, is I do not have it here. I have a previous. Okay, but of taking the minimum value of all the limiting functions, we can do this because in general the composition of organisms are nearly constant, and we can do that because, as I told you, essentially the nutrients or the elements that are fundamental for phytoplankton growth are carbon, hydrogen, oxygen, nitrogen, phosphorus, silicates, and sulfur. Of course, this comes from the fact that the general, if you want, a general way of representing an organic molecule, you may recall the story of sugar or carbohydrates, C6H12O6. Then, by the principle of fixed stoichiometry that tells us that the composition of organic matter is in general the same, of all organic matter is more or less the same, we can employ this kind of schematization. By employing the fixed stoichiometry model, we may then try to describe the limitation or limiting effect by introducing a function that we have already seen several times, that is the Michaelis-Menten function. This is the way that typically we employ for describing nutrient limitation, so that we have, let's give a look at this function, so that we have that the limiting function due to a nutrient is equal to the concentration of a nutrient divided by the concentration of a nutrient plus a constant K that is called the semi-saturation constant. So when the nutrient concentration is equal to K, the limiting effect is so that the maximum growth rate is exactly half the maximum growth rate. Please note that in this case, we are employing nutrient concentration in the external environment. So nutrient concentration outside the cells. Again, in this case, we may have various ways. For example, let's concentrate us on phosphorus and nitrogen, that are the two main nutrients that we shall take into account. We may have a multiplication or a synergetic effect, so that we may multiply this function. As I told you, in this case, you're probably overestimating limiting effect, or we may take a Liebig's approach, Liebig's law of minimum. So we just include into our model what are the most limiting nutrients, so the smallest of the limiting functions. This is why you take the minimum. In this case, while in the first case we are a little bit overestimating limiting effect, in this case we are a little bit underestimating limitation effect, because we are simply considering, we are only considering the most limiting nutrients. This approach may be extended to a quite a complex, large set of different nutrients, like the case in which here we are combining colimitation, you, for example, nitrogen, phosphorus, carbon, silicates, and so on. Again, there are two ways of combining. There are several ways, but there are three main ways of combining this limiting effect. One is the first one is multiplication. Second one is the Liebig's law of minimum. Third one is that of taking an harmonic mean, or that of taking classical arithmetic mean. I recall you that in these cases, the limiting function, for example, the cases we are presenting here, are all described by Michaelis-Menten approaches. So these are saturation curve. Why do we employ the Michaelis-Menten? You may recall that the Michaelis-Menten function is obtained when we describe enzymatic chemical reactions. Enzymatic chemical reactions have a particularity of depending on the presence of one enzyme that foster or speed up the reaction, the chemical reaction. In particular, when we are treating with living organisms, like for example plants, given that the number of offsprings produced by one organism is proportional to the number of organisms itself, we may implicitly assume that the algae itself is the enzyme. So more algae, more quick will be the growth rate of the population. Of course, this brings us to a description like this one. It is a saturation-like behavior. Again, as I told you, we employ the Michaelis-Menten formulation, and we say that Kn, the semi-saturation constant Kn, is the concentration of nitrogen, so that the speed rate or the limiting function has exactly value of 1/2. This is a saturation process. We have said that when we are going to calculate the effect, the limiting effect due to nutrient, we typically employ a concentration of external nutrient concentration. External to what? External to the cell. So that we are including the concentration of nutrient into the water column, essentially, to the water environment. But there are some cases in which you need also to include the concentration of nutrients into the cell. This is the case when you want to describe a process that is a two-step process, more sophisticated, for describing growth dynamics. In this case, the two-step approach, you separate the process of growth into two sub-processes. One, we may call it uptake, that is influenced by the external concentration and also by the internal concentration of the nutrients, internal in the cell. And a second part of the process, the second step, is the growth process and on the internal quota. In this case, if we indicate with a small q concentration, internal concentration with capital C concentration in the water column, external concentration, then we may propose these three models that are typically employed when you want to describe these kind of processes. The first one, it is a Michaelis-Menten approach in which the variable is the distance from the minimum internal contribution, the minimum internal concentration allowing algal growth, or we may also employ a Michaelis-Menten approach in which the semi-saturation constant is exactly equal to the concentration, minimum allowed concentration, internal concentration, or a classical linear approach. You may ask yourself why we shall complicate our life this way. Because unfortunately or fortunately, these processes really happens in nature. What we are trying to describe when we are introducing the two steps growth dynamic, we want to describe the fact that when there is a lot of nutrients, algae tend to store a quantity of nutrients into the internal part of their cell. This is called luxury uptake. Uptake of elements, uptake of nutrients. Uptake of nutrients that are influenced by internal and external concentration. So in this first part, we have both the external and the internal concentration, while on the second part, the part describing growth, we only take into account the internal concentrations, because these are the concentrations that are responsible of defining the growth speed. In this case, as I told you, you may say, why should we complicate our lives? And this is why I show you these are experimental data, which we have triangles representing phosphorus concentration, crosses that are nitrogen, assimilating nitrogen, and with continuous line describing chlorophyll A concentration. So with in this line, we describe concentration of chlorophyll. And what is happening here is interesting to note, is that we have a growth of the algal concentration, chlorophyll A, in the beginning of the spring or off-spring season. So in spring, we have a significant growth. In this case, we have a depletion of the nutrient available into the system, so that when the nutrients become very low, we have a dying of the algae, and we may observe a second significant algal bloom that happens in late spring. So these are, I recall you, but these are experimental data referring to a lake. So we are seeing, by looking at this data, we see that we have a first growth of first algal bloom in spring. This first algal bloom increases the number of algae. The algae start consuming nutrients like nitrogen and phosphorus. So we have a strong depletion of nutrients. But then something strange happens, and this happens very often in a real system, in which you have a second bloom, late summer, end of summer, second bloom. And you may ask yourself how it is possible, given that the nutrient concentration is decreasing. And the answer is that in this second bloom, the algae are employing well luxury uptake storage. So what they have stored in the inner part of the cell when the nutrients were abundant. So a two-step process, or then we should, before going to the phosphorus cycle, make a short discussion about nutrient bioavailability, because not all nutrient forms are bioavailable at the same level. For example, we may distinguish between the two main nutrients, nitrogen and phosphorus. We know that nitrogen may be in organic or inorganic form. The organic may be dissolved or particulate. So this is a dissolved organic matter, DOM, or this is particulate organic matter, or the inorganic form may be ammonium, nitrate, or nitrate. These are the main bioavailable forms of nitrogen. In particular, the really available forms of nitrogen are the ammonia nitrogen and the nitrate. I recall you that ammonia is NH4 minus or NH4 plus, sorry, and nitrate is NO3. So if you simply think at the dimension of these molecules, you may recognize that oxygen is quite a large element, so NO3 is much larger than NH4 in terms of molecular dimensions. This means that it is much easier for NH4 to cross the cellular membrane and to enter into the cell. So that if you have ammonia and nitrate, you shall expect that your ammonia pool should be exhausted, should finish first, and then when no more ammonia is available, then the algae shall turn in consuming nitrate. For the phosphorus, again, we shall consider two different forms of phosphorus, organic and inorganic phosphorus. For the organic forms of phosphorus, we have a dissolved and particulate, DOM, dissolved organic matter, and particulate organic matter, POM. And then for the inorganic forms, we have orthophosphates or polyphosphates. We know that orthophosphates are the more bioavailable because in terms of, again, of molecular dimensions, they are much easier to be absorbed or to pass the cellular membrane than polyphosphate. Lately, it has become clear that also there is an important quota of nutrient in terms of phosphorus, that is the so-called colloidal phosphorus. Colloidal phosphorus is a form that is linked to sulfactant. It is a typical form of phosphorus that you may find in a wastewater treatment plant, and it is a form that is recognized as to be an available form of phosphorus. How do we decide which is the limiting nutrient? You may recall that there is a quantity that is called a red-free ratio. Red-free ratio is the quantity of nitrogen concentration divided by phosphorus concentration. It is a way of measuring the availability of the two forms of nitrogen and phosphorus, of the two forms of the main forms of nutrients, nitrogen and phosphorus. You may recall that the red-free ratio, it is equal to 16 in moles, or it is equal to 7 in weight. And according to the definition, that is this one, you may say that if the red-free ratio is larger than 7, then there is a lot of nitrogen, and then phosphorus is the limiting nutrient. If the red-free ratio is smaller than 7, then nitrogen is the limiting nutrient. As rules of thumb, we know we apply generally is that in freshwater ecosystems like lakes or rivers, the limiting nutrient is phosphorus, while in saltwater ecosystems like coastal zones or seas, the limiting nutrient is nitrogen. Of course, the limiting nutrient concept is a relative concept because it means it is limiting the nutrient, but it is less available. So, for example, in the case of coastal zones, the limiting nutrient is nitrogen because we have a constant, strong supply of phosphorus. And this constant, strong supply of phosphorus comes from the sediments. In this case, This is why in coastal zones or in brackish saltwater ecosystem, nitrogen is limiting because phosphorus, there is a lot of phosphorus already, or there is a phosphorus source. We may apply with criteria for deciding which is the limiting nutrient because we apply the concept of fixed stoichiometry. Fixed meaning that a general way of representing biochemical molecule, biochemical substances, is this way in which you say that carbon, hydrogen, oxygen, and nitrogen and phosphorus are present in organic matter with these ratios. Often, the red-free ratio may be calculated by making the ratio between total nitrogen, total phosphorus, etc. But we now start understanding that not all forms are equally bioavailable. And then we may also understand that there may be processes like the two-step dynamics in which there are some hidden sources of nutrients, like for example in the two-step dynamics, luxury uptake, that is a hidden source of nutrients that may change the nutrient limitation effect. And then we may also consider that even if the concentration in water is very low, uptake could also be balanced by other processes, like for example, the suspension fluxes from sediments. The limiting nutrient could be harder to reduce than others. For example, phosphorus in lakes, it is harder to be reduced. This is why the limiting nutrient is also linked to that nutrient that is harder to reduce. In this case, we may have a more sophisticated approach for measuring limitation. Co-limitation is that of the Platt index. We have two forms of the Platt index: an absolute form and a relative form. The absolute, or better, the relative, we normalize the variation of increasing the growth rate as an increase of a nutrient, nitrogen, for example, and we normalize it by dividing by the total quantity of nitrogen. These indexes are a more sophisticated way of evaluating the effect of co-limitation. In particular, in this case, we may write that if mu, or the growth rate, is equal by constant times the combination of two forcing function, to the limiting function Fn and Fp, in which Fn and Fp are described like a Michaelis-Menten, then you may define the Platt index as the relative normalized ratio between the sensibility of the growth rate to the presence of nutrient. What we are doing here, we are simply measuring the sensibility of the growth rate, the sensibility of the growth rate to the variation of the concentration of nutrients. Of course, there are also the cases of limitation due to other nutrients. Typically, the example that we will discuss now is that of silicates or silicon. Silicon, it is an oligo element that may be relevant in certain species of algae, in particular for the diatoms. I recall you that, let me see if I'm able to get back to the first slide. Diatoms are those complex algae that we were discussing before. We have the pictures. Let's see why. Eccolo qua. Diatoms are algae that contain a structure, an internal skeletonic structure that is made up of silicates, essentially. This is why silicon may be a limiting nutrient for diatoms. It is clear, for example, if we look at this data, these are again experimental data in which we are measuring or comparing the quantity of algae, this is the violet curve, with the availability of silicon or silicates. We say that in this case, again, these are experimental data. We have that chlorophyll A, we have the first bloom of chlorophyll A in a spring. Then chlorophyll A starts to decrease, meaning that the algae are dying. And if we compare the chlorophyll A with the silicates concentration, we realize that algae are dying because silicates were totally consumed here. So we have an effect, a limiting effect, due to the fact that diatoms are the most diffuse algae in my system, and diatoms depends dramatically on the presence of silicates. There are some examples of silicon limitation. In these cases, we have, for example, we are plotting here the ratio silicon over nitrogen as a function of time. For example, these are three systems. This is the Irish Sea. This is the Mississippi River. What we are realizing here, for example, let's give a look to the Mississippi River. We know that going from the 60s up to the 90s, we have a completely different behavior in the sense that the ratio silicates over nitrogen tends to decrease and to become constant. And this is a typical effect of silicon limitation due to the fact that there is a lot of nitrogen loads into the system. So nitrogen is not limiting anymore because there is a lot of nitrogen coming from pollution. And the fact is that in this case, silicon is becoming the limiting nutrient. This is also a case in the Bay of Brest. These effects are reported into this interesting paper of Clorn, our evolving concept of coastal eutrophication. The point is that in both these systems, if we have such an effect, a limiting effect due to silicates, then we are for sure dealing with algae that need silicon to grow. And so this means that we are dealing with diatoms. Sorry, but I wanted to show you, before going to the last, the picture, because just to recall you, momento. (2020, 2021). E dove l'ho messo? Non trovo più. Eccolo qua. I just wanted to show you this nice picture because these are examples of diatoms. So you see that these algae, build quite complex structures, silicate skeletons or scaffolders that keep on the structure of the algae. So silicon, as you can imagine, by this kind of type of picture, is a very relevant element for the growth of these algae. Okay. Let's go back to a silicon limitation. Okay, now we finish our algal growth model by introducing the very simple aspects that deal with zooplankton. In this case, we are not modeling anymore plants or algae. Instead, we are describing explicitly the effects of grazing due to higher trophic levels. Zooplanktons are animals like this one, but feed on phytoplankton. Again, we have several ways of modeling these effects. In general, we may say that we have a reference the effect, but depends again, as always, by the temperature. We may include the mortality due to grazing into the mortality terms, like, for example, by splitting these terms into a non-predatory mortality and into a term that depends on the quantity of zooplankton. We have essentially two different types of zooplankton. We call it filter feeders, that are zooplankton that stays well with the mouth open, and so they filter the water that crosses, enter into their mouth. And on the other end, we have other type of zooplankton that are called grazers. Grazers are able to go around and chase for their own food. So remember that we are talking of animals here. We are talking of like these small crabs. In the case of filter feeders, we may write that the grazing effect is proportional to the quantity of algae to the quantity of zooplankton, and there is a limiting effect to a limiting function of G that normally depends on the temperature. For grazer, instead, we do not have a dependence on the concentration of algae because grazers are able to go around and to look for their own food. So this is the way we include the effect of the higher trophic system, the higher trophic levels. So we may say that the variation in time of the concentration of zooplankton, the Z in the T, is equal to a series of terms, again, an additive term, which is the growth rate of zooplankton minus respiration minus exudation minus non-predatory mortality times multiplied concentration of zooplankton minus the effect of grazing due to a higher trophic level. So the schema is again the same. Of course, we do not have settling here because these are animals that are able to move and to fight against gravity. So the settling effect is not so relevant. Okay, let's conclude this lecture by discussing quickly the phosphorus cycle. We said that of various elements that are key elements for life, phosphorus is one of these, one of the 5 most important elements found in living organisms. 60% of bones are phosphorus, calcium phosphate also found in soft tissue and so on, but also the genetic material is made up of phosphorus like ADP, ATP, and so on. I recall you that ATP is the adenine triphosphate and is the molecule that carries energy inside the cell. Phosphorus cycle is affected by anthropic activity in terms, for example, of agricultural uses of fertilizers, but also in the industrial processes, like, for example, detergents and medicines and so on. It is interesting to give a look to the effect on the phosphorus concentration on fish stocks. For example, here we have a decreasing phosphorus loads and aquatic ecosystem productivity. In red here, we are describing phosphorus concentrations. Phosphorus concentration, while in blue, we are describing the kilograms of sardines that are debarked from vessels that are doing fishery. These graphs are interesting because, for example, here we can see that there is a strange effect of fishing that stops between the 74 and the 79. You may recall that we had an energetic crisis in the late 70s in Europe, so that we did not have oil, or we have a problem in supplying with oil all the industries. And this is, for example, reflected by the catches in terms of sardine. And then we have, for example, other anthropic effects like this one, the one from the 89 and the 92, in which we have a zero contribution in terms of debarked quantity of fishery in terms of sardines. These are data referring to the Adriatic Sea. And of course, you may recall that between the 89 and the 1995, 1992, we have the war in Croatia and the ex-Yugoslavian republics war. So we had a strong stop in fishing activity, and this stop is reflected in the quantity of fish. Nevertheless, the stocks are covered due to the fact that we have a constant load of nutrients into the Adriatic. This is orthophosphate in red. But then we had another effect due to phosphorus, that is evident in the mid-80s, the so-called phosphorus ban, P-ban. Phosphorus ban that was a directive from the European Community that forced all member states to take away phosphorus from detergents. In this way, we have a decrease in the phosphorus loads, an evident decrease in the phosphorus loads in the 80s, and to this decrease in the phosphorus loads, we have a corresponding also decrease in the sardine that were fished in the Adriatic Sea. Okay, the phosphorus cycle is a slow sedimentary cycle with no gas phase, of course. Inputs come, for example, by mining. There is a storage that is in the rock and sedimentary deposits in the bottom of the sediment. And then we have some kind of shortcuts that transports phosphates from marine sediments up to the phosphorus cycles into animals. These cycles needs millions of years. So the movement from the marine sediments onto a water column of phosphorus may take millions of years, so it may take a very long time. Phosphorus storages, 0% is on the earth, 0.1% is on the earth crust, various form of calcium, calcite forms, magmatic and metamorphic rocks. The phosphorus processes in the environment are strongly dependent on the pH. For example, the transformation of phosphorus from this form. This graph describes the effects percent of phosphates in the various forms depending on the pH. So, depending on the pH, you will find your phosphorus in different ionic forms, or PO4 minus, or PO4 2 minus, or PO4 3 minus, and so on. Typically, in cultivated soil that are more basic, you will find phosphorus in the PO4 2 minus forms. I'm not going to, we already talked about colloidal, but last thing you should recall is that phosphorus is strongly absorbed by particulate, so that it is accumulated in the lithospheres by adsorption. It is a physical reversible process, and it is a chemically irreversible or partially irreversible process. The adsorption, so, is the movement of phosphorus from the dissolved quota in the water column onto the particles. Okay. I think yes, the only thing I would like just to stress before finishing is that the cycles of phosphorus or nitrogen have completely different timing. In particular, the cycle of phosphorus is much quicker than the cycle of nitrogen. As you see from these figures, cycle of phosphorus takes 15 days. So this means that on the surface of the Earth, on the cycles between the four spheres, hydrosphere, lithosphere, atmosphere, and biosphere, takes 15 days for the phosphorus and 40 days for nitrogen. This means, for example, you have to take into account this when you are evaluating limitation through Redfield ratio. Time scales are relevant in order to introduce a correct Redfield ratio corrections, because you have to include the fact that phosphorus becomes much quickly available than nitrogen. It is much quicker to become available than nitrogen. Okay, then I have proposed you, this is the Casey Star model of nutrient abatement in wetland. This is a Cadleck model, a very general model, but it is applicable to several pollutants. It can be used, for example, nitrogen, phosphorus, suspended solid, bacteria, and so on. And it is a very useful model that links the efficiency in abatement, in pollutant abatement, with the surface made available to a wetland system to expand. So we have a relationship between Q, that is the specific hydraulic load, the average flow, and the surface of the wetland, but may act by reducing these pollutant concentrations. Okay, sorry, I have to stop here now because I have another conference, and I hope it is everything clear. From next week, you shall start working on MATLAB. So you shall do with Alberto, you shall introduce your application of model for living systems, environmental systems. Okay, do you have any questions? If you do not have any questions, then I will close my lecture here and I wait for your question by mail. Otherwise, we will meet next week. We will continue next week.
Thank you.
Okay.
Bye.
Bye-bye.